Welcome to Lecture 4, a pivotal moment in your programming journey. Today we move from writing simple scripts to designing structured programs. The topics are decomposition and abstraction, and the primary tool we use to achieve them is the function. This is where you learn to write code that is not just correct but also clean, reusable, and understandable. We have a clear agenda. First, we'll explore the core ideas of structuring programs and hiding details. Then we'll dive into functions as the mechanism to do this. We'll learn how to write them, focusing on the critical distinction between return and print. We'll understand the important concept of variable scope, what variables a function can see. Finally, we'll touch on the advanced but powerful idea of using functions as arguments to other functions. By the end, you'll see how decomposition and abstraction together make complex programming manageable. Let's start with a fundamental shift in perspective. In programming, more code is not necessarily better. 1,000 lines of messy, repetitive code is worse than 100 lines of clear, well-organized code. We measure good programmers not by the volume of their code, but by the amount of functionality and clarity they achieve per line. Our goal is to write less code that does more. How? By avoiding repetition and creating reusable parts. This is where functions come in. They are our primary mechanism to achieve decomposition, breaking a problem into parts, and abstraction, hiding the complex details of those parts. To understand these concepts, let's use a perfect analogy: a digital projector. First, think of a single projector as a black box. You don't know how its internal optics and electronics work. You only know its interface. You plug in an HDMI cable, input, and it displays a magnified image on the wall, output. This is abstraction. You don't need to know how it works to use it effectively. The complex details are suppressed, allowing you to think at a higher level. Now, imagine projecting a massive image for an event like the Olympics. One projector isn't enough. The task is decomposed across multiple projectors. Each projector handles a slice of the total image. One takes the left input, another the center, another the right. They all work simultaneously. This is decomposition, breaking a large complex goal, showing a giant picture into smaller, manageable, and parallel tasks. Each unit is a self-contained black box abstraction, and they are combined to achieve something greater, decomposition. How do we translate this to programming? Instead of separate devices, we create separate modules of code. In this lecture, our modules are functions. These functions are self-contained pieces of logic. We use them to break up code that would otherwise be one long, intimidating script. They are intended to be reusable. Write once, call many times. They keep code organized, grouping related operations together. And they keep code coherent, meaning each function has a single, clear purpose. Decomposition makes a large program a collection of small, understandable pieces. Later, we'll achieve even more powerful decomposition using classes. But for now, functions are our essential building block. Alongside decomposition, we have abstraction. Going back to the projector, the user manual doesn't explain quantum physics. It explains the interface, which button turns it on, which port is for input. In programming, we treat a function as a black box. When you use it, you cannot see the details of its code unless you go looking. You do not need to see details to use it correctly. In fact, you do not want to see details. You want to focus on your own problem. This hides tedious, complex, or mathematical code behind a simple name. How do we document this interface? With a function specification or a docstring, a plain English description right above the function code that says what it does, what it takes, and what it returns. Formally, a function is a reusable chunk of code with a name. It's not run when Python first reads it. It's only executed when it is explicitly called or invoked in your program. Think of it like a recipe in a cookbook. The book can contain a recipe for bread, but you don't start baking just by having the book open. You have to decide to make bread and follow the steps. A function has key characteristics. It has a name. It has parameters. 0 or more inputs listed in parentheses. It should have a docstring. Highly recommended. It has a body, the indented block of code that does the work, and crucially, it returns something, a result value it sends back to the code that called it. Let's see the syntax. You define a function using the def keyword. Look at the example is even. We write def is even I. This names the function is even and says it takes one parameter I. Right after the definition line, we write a triple quoted docstring. Then monod input I, a positive int. Returns true if I is even, otherwise false that passed. This is for humans. Then the body. Print inside is even, is a diagnostic message. The core is the return statement. Return I%2 me is you. This expression I%2 me you evaluates to either true or false. That Boolean value is what the function gives back. To use it, you call it result ye is even 4. This passes the value 4 to the parameter I, runs the function's body, and assigns the returned true to the variable result. The print inside the function runs first, showing inside is even, but the value of the function call is what comes after return. This leads to a vital concept, scope. Scope is the mapping of variable names to objects within a certain region of code. When you call a function, a new temporary scope or frame is created. The formal parameter, like x in def fx, gets bound to the value of the actual parameter, like 3 in f3. Inside the function, x refers to this new binding. Now consider this code. We have a global variable x $3. We call z the parsh fx, the value 3 is passed in. Inside f, the line x $x plus 1 changes the local x to 4. It prints in fx, x of worth 4, and returns 4. The key point, the global x outside the function is still 3. It was not changed. The function's x is a separate local variable. The returned value 4 is then assigned to z. Scope ensures that functions are isolated. They don't accidentally mess with variables in other parts of your program unless you explicitly design them to. This is one of the most common points of confusion for new programmers. The difference between return and print. They are fundamentally different. Return is an exit and data passing mechanism that only has meaning inside a function. When a return statement is executed, it immediately ends the function's execution and sends a value back to the caller. A function can have multiple return statements, but only one will ever run per call. Any code in the function after return is ignored. The returned value can be stored in a variable, used in an expression, or ignored. Print, on the other hand, is a side effect. It can be used anywhere. It sends text to the console. You can have many print statements in a function. Code after a print continues to run. Print does not make a value available to the calling code. It just displays it. A function that only prints is often useless for computation because its result can't be captured and used later. A good function typically returns a value. You can then choose to print that returned value if you wish. Remember, return for data, print for display. Now for a more advanced but incredibly powerful concept, functions as arguments. In Python, functions are first-class objects. This means they can be assigned to variables, stored in data structures, and crucially passed as arguments to other functions. Look at this example. We have 3 functions. Func_parch A prints a message and implicitly returns none. Func_bash B takes a parameter y, prints a message and returns y. Func_bash_c takes a parameter z, prints a message and then does return z. It calls z as a function and returns its result. Now look at the calls. Print funca calls funca, which prints inside funca. Then print outputs the returned value, which is none. Next, print 5 plus func b2. This calls func b2, which prints inside func b and returns 2. Then 5 plus 2 is 7 and print outputs 7. Finally, print func c, func I. Here, func A, the function object itself, is passed as an argument to func C. Inside func C, Z is now an alias for func A. The line returns Z, therefore calls func A. This prints inside func A again and returns none to func C, which returns it to the outer print. This demonstrates remarkable flexibility. We can write functions that operate on other functions, enabling patterns like callbacks, wrappers, and higher-order logic. Let's bring it all home. Decomposition and abstraction are powerful individually, but together they are transformative. Decomposition lets us divide a problem into bite-sized pieces. Abstraction lets us forget the details of each piece once it's built. The glorious result? Code can be used many times but only has to be debugged once. You write and test a function thoroughly. Then, every time you call it, you can be confident it works. This saves immense time and reduces errors. It turns programming from a repetitive chore into a creative act of assembly.